transforming a cubic function. None of your transformations are going to change. So if it was a vertical stretch before, it's a vertical stretch. That's why you have your organizer out. All that information is the same as what it always was, okay? The difference is we're going to use a new parent function. So first, we're going to just talk about two problems where we don't have to graph. Then when we get to the graphing part, we're going to put the quadratic and the cubic function in your organizer. And then we're going to do a couple examples of how this would work for a cubic. And then we're going to let you guys try some. And while you guys are working on some, we're going to walk around and stamp homework 7 and homework 9. Does that make sense to everybody? Okay. So what cubic function do you obtain by applying the following transformations to y equals x cubed? So this is the parent function for a cubic. So that's what we're starting with. But we want to apply these transformations. We want to vertically stretch it by a factor of 3. We want to reflect it over the x-axis, and then we want to vertically translate it 5 units up. Okay? So with our parent function, it says this. This part is considered the inside of the function, the part that's being cubed for the cubic. And anything that's multiplying in front of that or added and subtracted beyond that cubing would be kind of the outside of the function where we said the vertical stuff was happening. So who has an idea of what I should put into this equation to incorporate a vertical stretch by 3? So where does the vertical transformation information go? Jared. Okay, good. Outside the parentheses. So basically, if I write something like this, that would be the same function, but vertically stretched by 3. I know that this is not part of what's being cubed because it doesn't have a power of 3 on it. It's not included in what's being raised to a power of 3. Okay. What would happen in order for me to reflect over the x-axis? So for reflections, what shows up in your equation that lets you know there's a reflection happening? Good, a negative. And now, if we want it to be over the x-axis, is that a horizontal reflection or a vertical reflection? Horizontal. Let's think. So the x-axis is horizontal. If you want to reflect something from above that to below that, did you just flip it vertically or horizontally? Vertically. So this is a vertical transformation or a vertical reflection. So should that negative that's multiplying our function be inside of what's being cubed or outside of what's being cubed? Outside when it's vertical, okay? So for a vertical reflection, you would see this, okay? I'll put them all together at the end, just trying to point out the separate ones to kind of review a little bit. Lastly, it says a vertical translation of 5 units up. Okay? So what's going to translate our function 5 units up? What are we going to have to do? Yeah. Good. You're going to have your x cubed, and then after that, you're going to add 5 to shift it 5 units up. So to shift this function 5 units up, we would add 5. So if this equation is supposed to incorporate all these changes, then really it would look like a negative 3 times an x cubed, and then plus 5. Notice that nothing is being cubed except for the x. That means there's no horizontal transformations included in this function. Does that make sense to everybody? Okay. So we're not changing any of the ways that any of the transformations work. We're just now doing them with x cubed instead of x squared. Anna? So if it was a horizontal stretch of 3, you would have a number inside of the cube, and it would actually be a 1/3 that's inside of the cube. Because remember, horizontal stuff is all a little bit off. So the number that's multiplied there, you use the reciprocal when you take it out to see what you're doing with the function. Okay? All right. Is this okay with everybody for the basic idea? So other problems that you might see on the homework besides graphing, and then we'll get to the graphing part. This should be review, okay? What is the quartic function with only 2 real zeros, x equals -4 and x equals -6? So how would we write a quartic that has these 2 real zeros? What are some options? Yeah.
X plus 4 x plus squared times x plus 6 squared.
Perfect. Okay. And technically, you could write some other options of this. Could you put a coefficient in here to multiply it? Yeah, it didn't say which way it faced or anything about the end behavior or stretching or compressing. So you could all have different numbers right here. Technically, could you have included another factor that gave you 2 imaginary roots instead of the real roots? Yeah, they didn't say anything about not having that. Squared because he wanted to make it of degree 4, because it says it's a quartic function, not a quadratic function. So if he just put x plus 4 and x plus 6, he would get the same zeros, but it would only be of degree 2. So by squaring each of them, he keeps those same zeros, but makes it of degree 4. Okay? Any other questions about that? It's kind of a review question, because we've seen the same theme throughout. All right, so in your organizers, let's put a couple of different functions. So you have all these doors. And so far, you only have the absolute value function on one of the doors, right? Yes?
For example 2,
Uh-huh.
is it possible for, for x plus 4 to have, a multiplicity of 3 and the other one to have a multiplicity of
Absolutely. Okay, yeah, good point. Did you guys get what she's saying? Okay, you didn't have to square each of them. You could do different multiplicities of whichever one you want. You just couldn't include any more real zeros than negative 4 and 6. But you could have kept just x plus 4, x plus 6, and then like x squared plus 5, which would have imaginary roots. You could have done stuff like that. So you had a lot of freedom there to write what you want. So you guys have one door with a parent function on it that's absolute value, right? Am I correct? We're all looking at that. Next to it, we're going to put another linear type of function that we're going to do when this unit is over. So we're going to keep that door blank for right now. Okay? And then below this, so below the absolute value function, we're going to put our quadratic function here, and then we're going to put our cubic here. Okay? So on the door for the quadratic function, we should have its title, and this should be review, but it is a polynomial function, so this would be a quadratic function. That's the type. Okay? Then what we did is we put a picture of the parent graph with the equation for the parent function also. What is the equation for the parent function of a quadratic? Good. Okay, so x squared is our parent for the quadratic, and anything else included with that x squared is some sort of stretch, compression, reflection, translation. Okay. And then we put the graph of the basic parent function. Where was the vertex for our parent function of a quadratic? Okay, good. 0, 0. And then we memorized a couple of points surrounding that, so we had the basic shape of the parent function and the correct width so that we could tell the difference when we stretched and compressed it and stuff like that. And so what we had said was 1 away from the vertex on either side is a point 1 above it, and then 2 away from the vertex on either side was a point 4 above the vertex. And that was our parent function. Okay. All right, what about the domain and range for this? So what is the domain for the parent function for the quadratic? I see Zeke's hand, but I know that he knows new people. Yeah, did he say? Good. All real numbers. Okay. Because looking from left to right along the x-axis, okay, there's no x value that if I pick it doesn't have a corresponding portion of the graph with it. Also, in the equation, you can plug any real number in that you want for x. You can square it and get a result. So every number works in this equation and yields a result. Okay, what about the range? I see hands of people, but they've all told me something today. I totally appreciate it. Don't get me wrong. But you guys have all told me an answer to something today. Yeah, Karen. Good job. So y is greater than or equal to 0. Okay, so graphically, the way that we see it, if we look for maximums and minimums, there is an absolute minimum to this function right here. It does not go below that. That means that all the y values for all the points along this function would all be y values greater than or equal to 0. Okay? All right, for interval notation, just to review this and keep it fresh in our mind so that when we see it later on, we know how to do it. Real numbers would be from negative infinity to infinity. Remember, this is not an x comma y. This is a for the x values, what is the minimum and what is the maximum. And since it's all real numbers, there's no minimum and no maximum, which is why you see the infinity symbols being used there. Okay. Then for the range, we're going from 0 to infinity. We can't exactly reach infinity. We do exactly reach n equal to 0, so we use that bracket instead of the parentheses. Okay? All right, so this should all basically be review, okay, of a quadratic. So now we want to fill in the same thing for a cubic and think about what a cubic looks like, okay? So on the door where the cubic will go, which is right below the quadratic, go ahead and label it as cubic. Oh, yeah. Kind of looks like QBO. Should say cubic. Okay. What is the equation for a parent function of a cubic? Quentin? Good. Okay. So f of x equals x cubed. Which is kind of the most basic cubic we could do. No extra terms, nothing multiplying, being added, subtracted. Okay. And so now let's think about what this looks like. Now this doesn't have a vertex in the traditional sense. It doesn't have one place where the graph completely turns around like the absolute value and the quadratic function. However, we want the point that's considered the vertex in a different sense, like the point that everything kind of revolves around, because when we stretch and compress stuff, we always stretch it from the vertex point, right? So we still have to know what that main point is. And for us, it's the point of the parent that kind of starts at 0, 0 for all these polynomial functions. So this is still going to have the point 0, 0, because when you plug in 0 and you cube it, you get 0. Okay, so this is still going to be our vertex point, but I'm using that word in kind of a different context. Do you guys understand it? That's just kind of the main point that we're going to stretch and compress everything from or reflect things around, okay? So 0, 0 is still that point, okay? When we go 1 away from that to the right, so think about if you took an x value of 1 and plugged that into this function, what would you get for the y value that goes with it? 1, okay? What about if you plugged in 2? CJ? 8. So you'd get something, I don't know if you guys have enough space to make 8. I can only do it if I really squish it. It'd be way up there, okay? Now, what if we plug in negative 1? So, yeah, if you cube negative 1, you actually get negative 1. And so then what about if you plug in negative 2? You get negative 8. So those ones might be too hard for you to graph. It's fine as long as you understand the concept of where they are. So this graph goes like this. Remember when we talked about that 0 of multiplicity 3, how the curve would cross through that 0 and look like it was going to turn around, but then not turn around and make that curvature? That's what the parent function of a cubic looks like. Okay? So now when you're stretching, compressing, and reflecting your graph, you have this point still at 0, 0. And it's these points that you can stretch and compress away from that point. Okay? All right, so there's not really a place for this in the note-taking guide. You can do this in the note-taking guide, or you can just do this on a separate sheet of paper. But we're just going to go through and do an example of how we would stretch, compress, reflect, translate this graph. Okay? Oh, I forgot one thing. Sorry. What did I forget on our little organizer? Domain and range, yeah. So sorry. All right, so what's the domain of this parent function for a cubic? Kyle? Good, all real numbers. So I can plug in any number and cube it, any real number, cube it, and get another real number. Or you can see, looking at the graph, there's nothing that you could pick. It might be really high or really low, but it will always correspond to a point on the graph. What about the range? Yeah, what? Good. All real numbers again. So unlike a quadratic, it doesn't turn around and have an absolute minimum or maximum, right? It continues forever up and down. No holes, no gaps, nothing like that. So all real numbers, okay? All right. Sorry that I forgot that. Okay, so here's a graph, okay, or an equation of a function. It's a cubic, right? So if I'm thinking about the parent function, when I see that it's a cubic, I'm thinking this, this, this. You don't always have to graph the 2, 8, because sometimes that's going to be a pain in the butt. Think about if that's stretched by 2. If you were 8 away from the vertex originally and you stretched it by 2, how many away from the vertex are you going to be now? 16? Like, That's going to be really hard to graph. So it's okay to just graph these 3 points as long as you know what the curve looks like, though. Don't draw me a line like this because it looks like it's linear. You know that it eventually goes down here and hits at like 8. So make sure that you express like how much curve is present in that parent function, okay? But I only care about if you have those 3 points, the vertex and at least one surrounding it. All right, let's list the transformations. How is this graph going to be transformed? Somebody give me a transformation you know is going to occur based on the numbers you see in the equation. Stephanie? Okay, so we're going to have a shift down to Austin. There's a vertical reflection. Quentin? Good. It's going to move to the left one. What haven't we listed? Okay, good. But it's not a stretch because it's a factor of 1/3. So if it's a factor of 1/3, it has to be a compression. Yeah. Okay. The right idea. Okay, so we have all these things going on. We have one horizontal movement right here. The rest are all vertical. We didn't really have a rule for the order in which we're going to do things. But if you're going to do a reflection and you're actually going to use the X and Y axis for your reflection, those need to happen before you shift it. That means like if I'm going to shift it left or right, if there's a horizontal reflection, I should do that before I shift it. If there's a vertical reflection, I should do that before I shift it up or down. Okay? So I'm just going to do the horizontal one first and then go through the vertical ones. Since there's no horizontal reflection, I can do the rest of the horizontal stuff. So the first thing I'm going to do is move everything to the left one. So my vertex will be here. The surrounding points will be one away and one up, one away and one down. Make sure I express the right curvature. Okay. So this is done. Yes, and I was going to mention that just in a little bit when we get to the end. All right, now I'm going to do all the vertical stuff. Okay. Some of you understand that really you can move it first if you reflect over the vertex instead of over the X or Y axis. But those of you that don't get that, if you want to be safe, you should just do your reflection first. Okay? So I'm going to go ahead and do my vertical reflection. The vertex is going to stay. It's not going to be reflected. But where there was a point above, that point is now going to move below. And where there was a point below, that point is now going to move above where the vertex is. Okay? So this point is going to end up down here. And this point is going to end up here. So that now the curve goes this way. Kind of an interesting fact about a cubic. If I just drew that, would you be able to tell for sure whether it was a horizontal or vertical reflection? So think about if it had been a horizontal reflection. This point would have gone over here. And this point would have gone over here. So you can't really tell. In the equation, you can tell, and you can name it based on where the negative showed up. But on the graph, if someone said write an equation and you knew it was reflected, I would have to accept answers that include both choices because it could be done either way. Okay? All right, so we've done the reflection. I'm going to go ahead and move it down to. Okay? So here's my vertex. I'm going to move it down to the points that are surrounding it. Okay, so I just took the yellow graph and shifted it down to. So that's done. And then to vertically compress it by 1/3, this is why it was really important that we know where the vertex is. The vertex doesn't move. Okay? But you're looking at the vertical distance of the points around the vertex. You're going to take how far they are currently, and you're going to times it by 1/3. So currently, this red point right here that's below the vertex, how many units is it below the vertex? Just a vertical distance. So here's the level of the vertex. This point is 1 unit below that. If I take that and multiply it by 1/3, I get 1/3. I'm redraw that point so that it is only 1/3 of a unit below the level of the vertex. So here's the level of the vertex. I'm going to draw it like right there, and I'm going to call it only a third of a unit below. Okay? So the same thing is going to happen with this other red point right here that's 1 unit above the vertex. Okay? It's 1 unit above. When I take that distance of 1 and multiply it by 1/3, again, I'll get 1/3. So I'm going to relocate this red point, okay? Not left or right, no horizontal movement, only vertically, so that it's a third of the unit above the vertex. Right there. So then that's going to cause my curve to look more like that. Okay? All right, I want to point out what Damien said because he makes a good check, and he actually makes another interesting way you could do this problem faster if you've caught on to how all the transformations work well. So he pointed out that our vertex point is no longer going to be at 0, 0. Where is our vertex point going to be? Look at the equation. -1, -2, because it only gets changed. It doesn't get stretched or compressed, right? So it only gets changed when you actually shift it. So it's going to end up at -1, -2. Is that right? Did we end up in the right spot? Yes. If you knew that ahead of time and you're really good at the transformations, you could just start your parent function right here and be like, oh, then these are going to flip and they're going to get compressed. And you could have it done really quickly. But if you're not at that place, you just need to, if you're drawing out all the graphs and you're getting there, but you don't understand the other way that I just mentioned, draw out all the graphs and get there, okay? Eventually you'll have done enough problems that you'll get there, but everyone's going to get there kind of at a different time. Does that make sense? Okay. But the more patterns you see, kind of the quicker it'll go. All right, we're going to do one that has a horizontal change in it also because we haven't really done any like that. So we're going to look at that here for our cubic, and then you guys are going to work while I stamp stuff. Okay, so how do I know this has more horizontal transformations in it instead of just a translation left or right? Stephanie? That the 1/2 is in there. And then here's a thing that's a little bit tricky. The 1/2 cannot stay how it's written. The way that it's written, that 1/2 has multiplied the x, and it's also been distributed to the number that was after x inside of the cube. Okay? So the problem is you need to factor it out. Not all the way out of the function. Just like you need to see the 1/2, and then you need to see what was being added or subtracted to x before the 1/2 kind of interfered and made it disguise. So you might look at this and you're thinking, oh, we're going to move 1 unit to the right. That's not correct, okay? Because that 1 is deceptive. That 1 is sitting there because it was multiplied by 1/2 and turned into 1. You want to know what it was before that happened, okay? So any number that's multiplying x, even if it's just a negative or just a number, you want to think about if that was factored out of the stuff that's in the cube. You're not taking the 1/2 out of the cube. You're just looking at it separated from the terms x and the constant, okay? So this would be x. And what would be the second term in that set of parentheses with x? Negative. It wouldn't be 1/2. 1/2 times what would make 1? 2. So you can do this one of two ways. You either have to know 1/2 times what would give me back 1. The answer to that question is 2. If your brain doesn't work like that or that's a little bit complicated for you, here's like the structure of what you could do every time. Take what was there, divide it by what you're factoring out, because that's what you're doing. You're dividing that out. And 1 divided by 1/2 would be 2. Okay? All right, so now let's list our transformations. What's going to happen in this problem? So let's start with the horizontal stuff. Since we haven't done this for a while, let's try to categorize it. It's not as similar as the stuff that we've seen before. So let's focus on horizontal transformations. Quentin? Okay, but that's a vertical one. So we'll get back to that in just a minute. That's okay. Okay, I'm kind of making you guys look at one place first, just kind of on purpose. So horizontal stuff. Who can list for me a horizontal transformation that's going to happen? Yeah. Good. To the right, too. Not the right one like we might have originally thought in looking at the problem, but now that we've arranged it properly, to the right, too. So we're going to move to the right, too. What other horizontal transformation is going to take place? Anna? Okay, good. So here's what you guys need to do with the horizontal stretches and compressions. They're not as straightforward as the vertical stuff. We talked about this. It's on the back of your note guide. But here's kind of a quick way to do it. Take the number that's here. You know it's inside, so you know it's horizontal. If you're having a hard time deciding if it's stretch or compression because it's confusing compared to the vertical stuff, first write down the number that you're going to be multiplying by, and that can kind of tell you if it's a stretch or compression. Okay? With the vertical stuff, you multiply by the number that's there, exactly as it is. With the horizontal stuff, you multiply by the reciprocal. So this number says 1/2, but what am I going to be multiplying by? 2. If you're taking things and you're timesing the distance by 2, are you stretching them away from the vertex or compressing them closer to the vertex? Stretching, because the distance is going to get multiplied by 2. It's going to get doubled, right? So if you can come up with this number first, that number can always tell you what it is, okay? Once you've taken the reciprocal, if the number's bigger than 1, it's a stretch. If it's smaller than 1, it's a compression. But after you've written it down right here and already thought about that, okay? All right, so that'll be our horizontal stuff. What about our vertical stuff? Good. Okay, and again, if you're struggling with is it a stretch or is it a compression, write down the number first. Vertical, what you see is exactly what you get. It says times 3. You're going to do times 3. When you time stuff by 3 vertically, you're going to increase the distance from the vertex, so you're going to stretch it away from it. So there's also a vertical stretch. And what other vertical transformation will there be? Good. We'll move up 1. All right? So we're going to start with that new parent function. So the only thing that's new in all of this is that there's a new parent function we're starting with. But the compressions, stretches, reflections, that's all the same as how you were working with it before. So again, here's my parent function. And maybe we'll try to do this the way that Damien was talking about. Especially since there aren't any reflections, it won't get too confusing. Okay, so based on what he was saying and what you guys see here, where do you know your graph should end up? Where should the vertex end up in this final graph? Yeah. Good. Okay, right 2, up 1. My vertex should end up at the point 2, 1. So I'm going to go ahead and put that point in there right now. 2, 1. If those were the only changes that was happening, this is where the vertex moved, there would still be a point 1 over and 1 above it, and 1 over and 1 below it. Your graph just would have been moved there. Is that okay with everybody? Now, remember, this is your vertex point. The reason I'm pointing that out is because the other two, we've done this basically and this at the same time by changing where the vertex was. These two things are stretches and compressions. Will the vertex move with these transformations? No. The vertex is what you're going to measure the distance from, and you're going to either stretch away from it or compress towards it. So it's not going to move. So it's important to know this point is going to stay here. It's the points that are around it that are going to adjust. Okay? So let's think about where they're going to adjust to. So horizontally, we're stretching by a factor of 2. So currently, this point right here, how far is it horizontally from the vertex? 1 unit, right? Just looking at the horizontal distance, it's 1 unit away. When I multiply that by 2, how far is it going to be away now? 2 units. So redraw it 2 units away horizontally. So here is my vertex point. It was 1 unit away. I want to draw it so that it's 2 away. Okay. Lucky for me, this distance is the same, so I don't have to do any new arithmetic. It was 1 away. Now I'm going to draw it so that it's 2 away. And it looks like a horizontal stretch. Look at what's happened to your graph. It used to be this nice little skinny curve, right? And we've taken it and gone like this to it, stretched it out that way a little bit. Then the last thing we have to do to it is we have to vertically stretch it. So here's our vertex. That's where we're measuring from. Okay. This point right here. Yeah, don't even know why it's not working right now. Okay, this point right here. How far is it from your vertex vertically? 1 unit, okay, from the level of the vertex. I'm going to take that distance of 1. I'm going to multiply it by 3, giving me a new distance of 3. I now want to redraw this point, still lined up here. Don't want to move it left or right, but I want to draw it so that it's 3 units vertically away from the vertex. So if the vertex is at this level, I'm going to redraw this point 1, 2, 3, so that it's here. Same thing here. This point, 1 unit away from the vertex vertically. I'm going to redraw it so that it's 3 units away from the vertex vertically. 1, 2, 3. Notice that am I counting from where it was and moving 3 from there? No. I'm drawing a new point that is now 3 units from the distance of the vertex. I don't count from where the old point was, okay? I'm always counting distance from the vertex. And so then this will be my new cubic function. Okay? Is this all right with everybody?